it's a smooth manifold endowed with a distribution of hyperplanes, which is maximally non-integrable. It means that if you have a submanifold, which is everywhere tangent to the distribution, then the dimension of this submanifold will be at most half the dimension of the distribution of hyperplane. Another way to define the contact manifold, contact structure, is given by Darboux theorem, which says more precisely that if you have a manifold endowed with a distribution of hyperplanes, then this distribution is maximally non-integrable if and only if locally it looks like the standard contact distribution on R2n plus 1, given by the kernel of the one form dz minus the sum of yi dxi. And here you have a picture of how it looks in R3 for n is equal to 1. So yes, something I forgot to say, contact manifold are always of odd dimension for linear algebra reason. So this Darboux theorem says that in contact geometry, you don't have any interesting local invariants. Locally, everyone looks the same. So if we want to say something interesting, it will have to be about global properties that a contact structure confer to a contact manifold. And today we will talk about some of these global properties, interesting global properties we can deduce from a contact structure. And another thing that this Darboux theorem says is that contact geometry is very flexible. So more precisely, if you look at the group of symmetry of a contact manifold, it will be very big. So it's the group of contactomorphism, so diffeomorphism that preserve the contact distribution. You can put on it some natural Fréchet manifold structure and turns it into an infinite dimensional group. And the group of interest today won't be the whole group of contactomorphism, but contactomorphism that are contact isotopic to the identity, and that I denote by cont not, and then its universal cover that I denote by cont tilde. And the easiest way to think about this universal cover is to think about it as the space of contact isotopy starting at the identity, and then you identify two isotopies if they are homotopic relatively to endpoints. So, as I said, we don't have any local invariant, but do interesting global quantities, invariant global quantities exist. And a first statement is that invariant quantities cannot come from functions on tuple of points. And the reason is really easy. It's because the group of contactomorphism, actually, it acts m transitively on your manifold for any integer little m. And a concrete example where we can apply this statement and reason is if you look at a distance function. So distance function on M is a special kind of functions on couple of points. And any invariant distance has to be equivalent to the trivial distance. So you cannot have interesting invariant distance on the manifold M itself. And the proof is really easy. You take 2 points that are different on your manifold M, x0 and y0. The distance between them, you put it equal to c. And then for any over 2 points that are not the same, you can find a contactomorphism that sends the first one to x0 and the second one to y0, because the group of contactomorphism acts too transitively on this manifold. And then the distance between x and y will be the same as distance between phi of x and phi of y, because the distance has been taken invariant, and it is the distance between x0 and y0. So it will be equal to c. So the distance is constant. So it's not very interesting. And the morality of this example is that if we want to construct invariant global quantities that are interesting, we will have to look at submanifolds that exhibit more contact rigidity than points. On points, we have a lot of flexibility. We can send any tuple on any tuple. So we have to look for more interesting submanifolds. And of course, the submanifold we will look at today will be the Legendrian submanifolds. And Legendrian submanifolds are submanifolds that remember a lot about the contact distribution. And more precisely, what is a Legendrian submanifold? So it's a submanifold which is everywhere tangent to your contact distribution and which is of maximal dimension. So it will be equal to half the dimension of your distribution of hyperplane. So if your contact manifold is of dimension 2n plus 1, your Legendrian will be of dimension n. And I will look at the space of Legendrian that are Legendrian isotopic to a fixed Legendrian that I denote by curly L lambda, and also to its universal cover. So again, the easiest way to think about it, this universal cover, I think, is you look at all Legendrian isotopies, and then you identify two of them if they are homotopic one to each other, relatively to endpoints. And you have the group of contact homomorphism acts one transitively on the space of Legendrian isotopy, and the universal cover of the group acts one transitively also on the universal cover of the space of Legendrian isotopies. So now some examples that will be of interest today. So first I defined the first example I want to give is the odd contact sphere. So you take the odd dimensional sphere S2n plus 1. You can see it inside a Cn plus 1, so the space of complex number to the power n plus 1. And then the contact distribution here is given as the maximal subspace of the tangent space of the sphere, which is invariant by multiplication by the number I. So this is the contact manifold. And then a natural Legendrian inside it is just you take the small sphere Sn inside S2n plus 1. This small sphere will be a Legendrian. And actually, you have an antipodal action on the sphere, given by plus minus. And this antipodal action preserves the contact distribution. So when you quotient the sphere by this antipodal action, you get the real projective space, and the contact distribution descends to the real projective space, and endow this real projective space with a contact distribution. And the little sphere Sn also descends to this little RPn, which will be a Legendrian inside Rp2n plus 1. A second example I will be interested in today is the periodic one-jet bundle of a manifold X. So what I mean by periodic one-jet bundle, you take the cotangent bundle of X, and then instead of taking the product with the real line, as usual, you take the product with the circle S1. And here you have also a standard contact distribution on this space given by the kernel of the one form dz minus lambda, where lambda is the canonical one form of the cotangent. So in local coordinate, it's PDQ. So this is the contact manifold, and your Legendrian inside is just the zero section. And finally, a last example I will be interested in is you take a manifold X and you take its projectivized cotangent bundle, and this manifold carry a canonical contact distribution given here by the formula at the end of the line. And if you take any submanifold S inside X and you take the projectivized co-normal bundle of S, it gives you a Legendrian inside the projectivized cotangent bundle of X. Okay, so these are three examples I want to talk about today. And if you have no question, maybe I go a bit forward. So yes, do these Legendrian submanifold exhibit more contact rigidity than points? Can we say more interesting things about Legendrian? And of course, the answer will be yes. And first, I introduce some terminology. So I will say that the universal cover of the Legendrian isotopy class of Legendrian lambda is unbounded if it admits an unbounded invariant distance. And there is a striking result by Vincent Collin and Sheila Sandon in 2012 that say if you take the Legendrian to be the little real projective space inside the big projective space, you take the universal cover of its Legendrian isotopy class, then this space is unbounded. So it carries an unbounded invariant distance. And they also show that the same is true for the zero section inside the periodic one-jet bundle. So here you have some rigidity. You can construct interesting distance that are not just constant distance as on points. They can take arbitrarily large value. And I will just give some idea of the proof, or at least, yes, some flavor of the proof and construction they were giving. So in some sense, the distance, they construct a lot of distance, but I will describe just one of them that they call the discriminant distance. So this discriminant distance, in some sense, is a word metric. Okay, so the words here will be embedded Legendrian isotopies. So I will say that a Legendrian isotopy is embedded if it does not have self-intersection. So lambda t does not intersect lambda s if t is different from s. And then the distance between two elements, lambda tilde and lambda prime tilde, is the minimum number of embedded Legendrian isotopies I need to go from lambda tilde and to reach lambda prime. Okay, so the minimum number of Legendrian isotopies I need so that by concatenating lambda tilde by these Legendrian isotopies, I can reach lambda prime. So in some sense, what it counts, this distance, it counts Legendrian intersection. So what Legendrian intersection we cannot get rid of. So if these distances are unbounded, it means that we cannot get rid of a lot of Legendrian intersection in some sense. This is the rigidity it captures. And so a bit more concrete here, what is the unbounded sequence they choose for RPN? So for the real projective space, so on the real projective space, the rep flow is given just by Hopf vibration. So it's just the multiplication by exponential I pi t. And the rep flow then, it's a periodic isotopy of contactomorphism. So it comes back at the identity after integer amount of time. And if you apply the rep flow to this Legendrian, which is RPN, then after integer amount of time, this Legendrian comes back to itself. So you have an intersection. And again, if you go if you iterate two times the rep flow and apply it to this Legendrian, you cross this RPN two times. And actually, Vincent Collin and Sheila Sandon show that these intersections, you cannot get rid of them. Okay? And they use Giventhal's nonlinear Maslov index to show that you cannot get rid of them. So by applying the rep flow to this Legendrian RPN, your distance grows as the number of iteration of the rep flow. And a bit similar construction holds also for the one-jet bundle. Here they take also the rep flow. So here the rep flow is just the translation in the last coordinate. And again, the rep flow is periodic. So after integer amount of time, it comes back to the identity. And then with the same argument, not the same argument, but then again, if you apply the rep flow to the zero section, after integer amount of time, it comes back to itself. So you have an intersection. And they show that, Vincent Collin and Sheila Sandon, they show that you cannot get rid of this intersection by using some generating function techniques and also some spectral selectors that they deduce from existence of generating function. Actually, this was tools constructed by Sheila Sandon. And then they use these tools to prove that you cannot get rid of these intersections. And So if you have no questions, I just go to, yes, a bit more conceptually, what was important in these two examples. So first, there was this existence of a periodic rep flow. So in other words, you have loop of contactomorphism. So a loop of contactomorphism, so an isotopy of contactomorphism that come back to the identity. And more geometrically, what is a rep flow? It's just an isotopy of contactomorphism whose speed is everywhere transverse to the contact distribution. So if you look at the speed of a point under the rep flow, then the speed of this point will be everywhere transverse to the contact distribution. So this was one ingredient that we used. And another thing that was very important, actually, is that when we were applying the rep flow to a Legendrian, so we were getting a loop of Legendrian, but these loops of Legendrian were not contractible. Because if they were contractible, then the distance would not change. I don't know if you remember, it was just because we are looking at Legendrian isotopies up to homotopy. So if we have a loop which is contractible, then this loop, we just don't see it. So it was very important that these loops of Legendrian were not contractible. And more precisely, Eliashberg and Polterovich introduced some notion, and they called this kind of Legendrian spaces orderable. So what it means to be orderable, it means that positive loops of Legendrian, so again, a positive loop of Legendrian is a Legendrian isotopy whose speed is everywhere transverse to the contact distribution. And loop, it means that it comes back to itself. So positive loops of Legendrian are not contractible. And usually to show orderability, it's something hard. It is where the rigidity lies, actually, because you have to find obstruction to existence of a contractible loop. And this obstruction usually use generating function techniques, Giventhal's nonlinear Maslov index, or as we will see also, Legendrian contact homology. So it's yeah, this is where the rigidity lies in what we will say later. So, and actually, we got a generalization of the theorem of Vincent Collet and Sheila Sundon with Simon Allais some years ago. So if you take a contact manifold and you take a closed Legendrian inside it, actually the two hypotheses we were discussing just before are exactly enough to show that the space is unbounded. So more precisely, if the universal cover of the Legendrian isotopy class is orderable, so the positive loops of Legendrian are not contractible, and there exists a positive loop of contactomorphism, then L tilde is unbounded. Okay? So we recover the results of Vincent Collin and Sheila Sundon because in their examples, they were satisfying these assumptions, but we get some new examples of Legendrian whose universal cover isotopy, Legendrian isotopy class is unbounded. So for example, if you take any submanifold in the sphere Sn with sufficiently big codimension, then the universal cover of its Legendrian isotopy class. So here the Legendrian is the projectivized conormal bundle of this submanifold S inside the projectivized cotangent bundle of the sphere Sn. If you take its Legendrian isotopy class and you take its universal cover, then it is unbounded thanks to this theorem. And the proof goes as follows. Actually, Chernoff and Nemirovsky, they prove that the projectivized conormal bundle of this submanifold S is orderable by using also generating function techniques. And so we have the first assumption of the theorem. So the space is orderable. And moreover, you have a positive loop of contactomorphism, and this positive loop is just given by the cogeodesic flow. Okay, so no questions? Okay, and so recently I have a second generalization. So a generalization of the theorem we got, I just present with Simon Allais, which is the following. Now, again, we suppose that L tilde is orderable and there exists a positive loop of Legendrian. So by assumption, this positive loop is not contractible. And assume, moreover, that this loop can be extended to a loop of contactomorphism. Then L tilde is unbounded. So this theorem generalized the previous one because here I don't expect this loop of contactomorphism to be itself positive. It extends a positive loop of Legendrian, but it does not have to be positive everywhere itself, this loop of contactomorphism. Okay, and actually we have concrete example where we can apply this theorem A, but we cannot apply the theorem before. So it's a real generalization. It's not vacuous. So the corollary is like that. So a new example of Legendrian, which is unbounded, whose universal cover Legendrian isotopy class is unbounded, is given by this. You take an hypersurface torus, Tn minus 1 inside Tn. You take its projectivized conormal bundle. Then the universal cover of its Legendrian isotopy class satisfies all the assumption of theorem A, but it does not satisfy the assumption of the previous theorems. So this space is unbounded, and we could not deduce unboundedness from previous theorem. And the proof goes as follows. The first thing is that in the unitary, the projectivized cotangent, in the unitary cotangent of the torus, Chernoff and Nemirovsky, they have shown actually that there does not exist positive loop of contactomorphism. So this is why we cannot apply the previous theorem. Here we don't have positive loop of contactomorphism. But actually the projectivized conormal bundle of this hypersurface torus is orderable. And here you can use results of Colin, Chantraine, and Dimitroglou-Ritzel because this Legendrian is hypertight. And you can use this theorem to show that this space is orderable. And they use Legendrian contact homology techniques. And then the loop of Legendrian, the positive loop of Legendrian is just given by this loop. So you take the torus times t, and then you look at t for t going to 0 to 1. So you get a loop of Legendrian, and it's easy to compute that this loop is positive. And moreover, this loop extends to this loop of contactomorphism, given by just the translation in the QN coordinate. So this is a loop of contactomorphism that is, of course, not positive. So maybe you have a question here. I don't know. No? Okay.
Maybe I have a question. So why in this your theorem non-contractible is in brackets?
It's just because it's just to recall what is the definition, because L tilde is orderable. So of course, if I have a positive loop, this positive loop cannot be contractible by assumption.
I see. Okay.
So it was just to remind to remind that this
Thank
loop
you.
is yeah.
Okay.
Okay. Thank you. And okay, so now before going to the next theorem I want to present, so I want to show two theorems today. So this one and another one. And before showing, talking about the other one, I wanted to put a bit more historical context, maybe around theorem A, and also why I find it interesting. So first, the search for invariant distance started in symplectic geometry. The first one was constructed by Hofer. So the offer distance is a B-invariant distance on the group of Hamiltonian symplectomorphism. So here, for simplicity, I am assuming that my symplectic manifold W omega is closed. And this offer distance is a Finsler type distance. And it was constructed by Offer in the early 90s for R2N. And then, but yeah, it was generalized by Professor Polterovich and Lalonde MacDuff for every symplectic manifold. And then this offer distance on the group was in some sense generalized by Shekhanov to the relative case. So not on the group of Hamiltonian symplectomorphism, but on closed Lagrangian. So, and Shekhanov distance also was an invariant distance on the space of Lagrangians. And in contact geometry, the story is a bit the same. So first, people have constructed invariant distance on the group of contactomorphism, and then using these distances on the group, later we deduce some distances on space of Legendrian that we discussed before. So the story in contact geometry started with Sheila Sandon, who constructed an interesting B-invariant distance on the group of contactomorphism of R2N times S1. And interesting here mean unbounded. This is what I hear by interesting. And then Zapolsky, also using the same kind of technique, so generating function techniques, constructed B-invariant distance on the group of contactomorphism of the periodic one-jet bundle of a closed manifold X. Then Vincent Collin and Sheila Sandon constructed over distances on the universal cover of the group of contactomorphism of R2N times S1, and also the universal cover of the real projective space. And let's say finally, I think the most general results in some sense is the results of Fraser, Polterovich, and Rosen, where they construct B-invariant distance that are unbounded for any closed manifolds that admit periodic rep flow and no contractible positive loop of contactomorphism. And okay, so this is the story for B-invariant distance on the group of contactomorphism, and then the story for invariant distance on Legendrian spaces is the story I've just discussed before. So let's say the Vincent Collin and Sheila Sandon distance on cont tilde is the one was also called the discriminant distance that allows them to then define this discriminant distance on space of Legendrian. And then the distance of Fraser, Polterovich, Rosen is in some sense on the space of contactomorphism, in some sense is the one we considered with Simon Allais to construct our distance on the space of Legendrian. And some remark here is that in contact geometry, all the results about invariant distance happens when there is periodic rep flow, or at least a positive loop of contactomorphism. And the only results for the moment, interesting result, that does not make this assumption of existence of positive loop of contactomorphism is the theorem A I just shown before. And this is why I was a bit happy to have a result about invariant distance without asking for positive loop of Legendrian. So this was a first remark. And the second one is that all the distances, B-invariant distances on the group of contactomorphism and invariant distances on spaces of Legendrian, they were all taking discrete values, so integer values. And actually, Fraser, Polterovich, and Rosen showed that it has to be the case on the group of contactomorphism, as we will see more precisely later. And I shown that it has to be the case also for Legendrian. And this is the next slide. Okay. So, and in some sense, it's a remaining of the flexibility. We had some rigidity that allows to construct unbounded distance, but there's still lot of flexibility, more than in symplectic geometry, because in symplectic geometry you can have Finsler type distance. Here you have too much flexibility to expect Finsler type distance. So more precisely, if you have an invariant distance on the Legendrian isotopy class of a fixed Legendrian lambda, then there exists a positive constant C such that the distance between lambda and lambda prime is greater than C for any lambda which is different from lambda prime. And I have a similar statement for universal covers, but it's a bit more hard to state, so I just state the one for the Legendrian isotopy class. And yes, as I said just before, there is a similar result found by Fraser, Polterovich, and Rosen for the B-invariant distance on the group of contactomorphism. So there exists a constant C such that the distance between phi and psi is greater than C for any phi different from psi if your distance was B-invariant. Okay, so if you don't have any question, maybe I move to the proof. So now I want to prove this two theorem, or at least give some ideas of the proof. And before giving the proof, I want to talk a little bit more about orderability again. So we said that the universal cover of the Legendrian isotopy class is orderable if positive loops of Legendrian are not contractible. But why Eliashberg and Polterovich call it orderability? It's because actually it induces some partial order. And here I want to present this partial order. So if you take a co-oriented contact structure, so what it means, a co-oriented contact structure, one way to see it is to say that you have one form such that the kernel of the one form is exactly your contact distribution. Then I will say that an element, so a contactomorphism, so here I say contactomorphism just for simplicity, but contactomorphism here, it's an element in the universal cover. So I take a contactomorphism, I say that it is greater than the identity if and only if there exists a contact isotopy that represents it, such that the speed of this isotopy is non-negative. Okay, so this is the definition of this binary relation on the group con tilde. And then you can define the same binary relation on L tilde by saying that two elements lambda tilde is less than lambda prime tilde if and only if there exists phi tilde which is greater than the identity, a contactomorphism greater than the identity that sends lambda tilde on lambda prime tilde. Okay, so this is an easy lemma. Actually, this binary relation, so here I'm talking about the binary relation on L tilde. So the binary relation on L tilde is reflexive, it is transitive, and it is invariant by contactomorphism. So what it means to be invariant by contactomorphism, so phi lambda is less than phi lambda prime, if and only if lambda is less than lambda prime. So this is easy to check. What is interesting and hard to check is that antisymmetry of this binary relation is not always true. And if it is antisymmetric, then it is a partial order. And Eliashberg and Polterovich, and also Chernoff and Nemirovsky, they show that this binary relation is a partial order if and only if L tilde is orderable. So if and only if positive loops are not contractible. Okay, so this was just again some orderability that we will, because we will use it in our construction, this binary relation. Okay, so now just idea of the proof of theorem A. So theorem A is the construction of an unbounded distance. So just recall, it's the hypothesis of theorem A, or some of them at least. So you take a positive loop of Legendrian, lambda t, and then you take a loop of contactomorphism that extend it. So this loop of contactomorphism does not have to be positive everywhere, but yeah, it exists. You take a loop that extends it. Then some notation, I will denote by lambda tilde s the lift of the Legendrian isotopy lambda st. So s here is a fixed real number and t goes from 0 to 1. Okay, so you take lambda st and then you lift it to the universal cover. And phi tilde s is the same. You take a real number s, and then phi tilde s is the lift of phi st, and t goes from 0 to 1. And just to make sure that everyone agrees with the notation, so phi tilde s applies to lambda 0, gives you lambda s. This is just some notations. Okay, and then a first lemma, which I won't prove, but it's not very hard to prove. So for any element of the universal cover, lambda tilde, there exists an integer n such that lambda tilde is in between lambda n tilde and lambda minus n tilde. Okay, I won't prove it, but the idea of the proof is really easy. It just comes from the fact that lambda t is positive. So if you iterate it enough time, it will get more and more positive so that at some point it will be greater than lambda tilde. And the same is true for lambda minus n. Since it is positive, if you do it backwards, it will get more and more negative so that at the end it will be less than lambda tilde. Okay. So this was his lemma. And the second one, which is not very much harder, but I'll try to give a proof for this one at least. So for all lambda and lambda prime, there exists an integer n such that lambda tilde is in between phi n applied to lambda prime and phi minus n applied to lambda prime. So here the little more difficulty comes from the fact that phi t was not a positive loop. So by iterating it more and more times, I'm not getting more and more positive. So it was just extending a positive loop of Legendrian. But it's not hard to get rid of this difficulty. So yeah, proof of this second lemma. So first, yeah, you fix lambda tilde and lambda tilde prime from the lemma. And then you find a contactomorphism that sends the time zero of your positive Legendrian isotopy to lambda prime. And then by the previous lemma, there exists an integer n such that psi minus 1 lambda is in between lambda n and lambda minus n. But lambda n and lambda minus n, from the notation we introduced, it's just phi minus n applied to lambda 0 and phi n applied to lambda 0. Okay, and now what we do, we just multiply all this inequality by psi tilde. Okay, and we don't change the sense of inequalities because this binary relation is invariant. And now we use the fact actually that phi t is a loop of contactomorphism. So it comes back to the identity. So it means that phi tilde n for an integer n, it commutes with all the elements of the universal cover. Okay, because phi t is a loop, it comes back to the identity. It commutes with all the elements of the universal cover of the group of contactomorphism. So then I use the fact that it commutes with psi to get the last inequality. Okay, since it commutes with psi and psi lambda 0 is equal to lambda prime, we get the proof of the lemma. Okay. So now, if everyone agrees with that, I go to proof of theorem A. So now I assume, moreover, that L tilde is orderable. Then the map which takes two Legendrian lambda and lambda prime and associate to it the smallest n such that lambda is in between phi n lambda prime and phi minus n lambda prime, actually it is an unbounded invariant distance. And this is the unbounded invariant distance I was talking about. So for invariance, it uses more or less only the fact that phi n, since phi t is a loop, phi n commutes with elements of the universal cover. So it's more or less only that, and also the fact that the binary relation is invariant. So with these two ingredients, you prove invariance of this distance. Then non-degeneracy of this distance follows from the fact that the binary relation is antisymmetric, because we have assumed that L tilde is orderable, so the binary relation is a partial order, so it is antisymmetric. So if you suppose that the distance between lambda and lambda prime is equal to 0, it means that lambda prime is less than lambda, and lambda is less than lambda prime. So by antisymmetry, lambda has to be equal to lambda prime. So this is how you deduce non-degeneracy. And then triangle inequality follows from transitivity and invariance of this binary relation. And unboundedness, for unboundedness, the sequence you can take is just you take the positive loop, the positive Legendrian isotopies. So it's easy to see that the distance between lambda 0 and lambda n is just equal to n. N here is an integer. And here it uses also antisymmetry. So this is the proof of theorem A, or at least the idea of the proof. And some applications to study over distances. So yes, maybe I talk a bit quickly about, we can use this distance to study over distances. So for example, with Simon-Allais, and also this distance was independently constructed by Lucas Nakamura under this following assumption. So here you take L tilde to be orderable. So you just assume orderability of L tilde. You take a contact form and you take its rep flow, then you can define a pseudo distance that we call with Simon-Allais the spectral distance, because it has some geometric property also, which is the smallest t such that lambda is in between phi alpha t lambda prime and phi alpha minus t lambda prime. So it gives you a pseudo distance, but this pseudo distance is unbounded, but it is not invariant by contact homomorphism. And an easy way to make it invariant is just by taking the supremum with all contact. So the distance between lambda prime is the supremum of distance between psi lambda prime for all contact homomorphism psi. But then by doing so, maybe you just get plus infinity. And actually, if moreover, you assume that you are in the hypothesis of theorem A, so if there exists a positive loop of Legendrian and a loop of contact homomorphism extending it, actually this distance is bounded. So this distance here is bounded, and it is actually less than the distance I've just constructed. So with the hypothesis of theorem A, this map is finite. So maybe it will be interesting to see that if without this assumption of theorem A, does this map is still finite or not? So it will mean that only orderability of L would be enough to expect existence of unbounded invariant distance on space of Legendrian. But this I don't know for the moment. And okay, and I wanted to talk a little bit also how we can use this distance to maybe construct norms on group of contact homomorphism, but maybe I skip it, and if we have time at the end, I talk about it. So now maybe I go to the proof of theorem B. So theorem B was a discreteness of the invariant distance. So you remember, so discreteness means that if you have an invariant distance, there exists a constant c such that the distance between two Legendrians that are not the same has to be greater than this constant c. And again, here we will have two propositions to show this theorem. The first one is Weinstein neighborhood theorem, and it says the following. So if you have a closed Legendrian inside a manifold, then you can find a neighborhood of this Legendrian that is contactomorphic to the one jet bundle of this Legendrian. And moreover, this contactomorphism fixes the zero section. So it sends your Legendrian lambda on lambda. And here I identify the second lambda with the zero section. And let's say the classic Weinstein neighborhood theorem says that this contactomorphism is just between a neighborhood of the Legendrian lambda and a neighborhood of your zero section. But then you can use the contactomorphism that is in the title of the slide to extend this neighborhood of the zero section to the whole one jet bundle in some sense. Okay. So this is the first proposition. A second one is the following. So you take two sets, B and B prime. Here, B, I've colored it in red, B prime in orange. And you suppose that B intersect the zero section. Okay, these two sets are in the one jet bundle here. And you suppose that the red set, the B, intersect the zero section in a small chart of lambda, so in an open ball in the zero section. And B prime, you just assume it to intersect lambda. And if B lies above the intersection with the zero section, so if B is in this green cylinder and B is bounded, then there exists a compactly supported contactomorphism that sends B inside B prime. And moreover, this contactomorphism, it fixes the zero section. Okay, and the proof is not so hard, and it's pretty much easy even. So you take this, so B intersect lambda in a small chart, okay? So in this blue line here. But then, since it is in a small chart, you can find a diffeomorphism of lambda, so a diffeomorphism of the zero section, isotopic to the identity, that send the blue line, so the intersection of B with the zero section, with inside the purple line, okay, inside B prime, the intersection of B prime and the zero section. And then you can lift this, so you have a diffeomorphism isotopic to the identity of the zero section. You can lift this diffeomorphism canonically to the one jet bundle. So there is a way to lift diffeomorphism of the zero section to contactomorphism of the one jet bundle. And then this new contactomorphism of the one jet bundle, it will sense this B, the red line, inside the dotted red line above the dotted blue line here. And then at last, you just need to use the contactomorphism of the title of the slide. So in the title of the slide, you have a contactomorphism that shrink everything for t small enough. This contactomorphism shrink everything to the zero section. So by composing the contactomorphism we constructed with this contactomorphism of the title, you can send B inside B prime. And you can make everything compactly supported because everything was contact isotopies and B was bounded. Okay, so this was the two propositions that were the most important to prove theorem B. And then, yes, this is just a reminding of this notation. So I I have a Legendrian. I take a neighborhood of this Legendrian. I take a contactomorphism that send it to the whole one-jet bundle. I take a ball B which intersect the zero section in a small ball, and then I take curly B to be the corresponding set inside the original contact manifold. So curly B intersect the original lambda into a small ball. And the corollary of these two previous propositions is the following. If you take a distance which is invariant on the space of Legendrian isotopy, then for any contactomorphism which is supported in curly B, then the distance between lambda and phi of lambda is less than 2 times the distance between lambda and lambda prime for any lambda prime which is not equal to lambda. Okay, so let's prove this corollary. So you take lambda which is different from lambda prime. So there exists an open set B prime inside your initial neighborhood of lambda, which does not intersect lambda prime, but that intersect lambda. And then by the first step, by combining the two propositions of the first step, you can find a contactomorphism that sends B to B prime and that fix lambda. And so the support of the conjugate of phi minus 1 by this contactomorphism will be inside B prime, because the support of the conjugate is just inside the image of the support. But the support of phi was inside B, and psi of B is B prime. So the support of conjugate of phi minus 1 by psi is inside B prime. And then it's just some algebraic manipulation. So the distance between lambda and phi of lambda is the same as the distance between psi lambda and psi phi lambda, because the distance was invariant. But psi preserves lambda. So it's just the distance between lambda and psi phi lambda. And then you use the fact that you are a distance, so you have triangle inequality. So it is less than distance between lambda lambda prime plus distance lambda prime psi phi lambda. So the first term remains the same on the next line, but then the second term, you use again that the distance is invariant and you compose both sides by psi phi minus 1, psi minus 1. And then you reach the last line because psi phi minus 1, psi minus 1 has its support in B prime, but B prime, it does not intersect lambda prime. So this contactomorphism fixes lambda prime. And psi also fixes lambda. So the distance, the last term is just the distance between lambda prime and lambda. And then you use, yes, of course, symmetry of the distance. Distance between lambda prime and lambda is the same as. Okay. Do you have questions? Because I wanted to point at some time what I'm talking about, at what inequality or equality here I am, but I was not able to point it. So, okay, if no questions, I go, yeah, how to deduce from this corollary theorem B, then it's not hard. So what we want to show, actually, it's enough to show that you fix lambda and you suppose by contradiction that there does not exist discontent C such that distance between lambda and lambda prime is greater than C. So by contradiction, we assume that there exists a sequence lambda n such that each lambda n is different from lambda, and the distance between lambda and lambda n goes to 0 as n goes to infinity. And then you take this contactomorphism, so curly B, just recall, curly B is a small ball that intersects lambda in a small chart. But then you can construct a contactomorphism supported in curly B such that phi lambda is different from lambda. You just push a little bit lambda in this small chart. And then, so since the phi lambda is different from lambda, the distance between lambda and phi lambda is strictly positive, but at the same time, the corollary said to us that the distance between lambda and phi lambda is less than 2 times the distance between lambda and lambda n for all n. And so you have a contradiction because this sequence goes to zero, but at the same time, it is bounded away from zero by a constant. So this is the contradiction, and it gives the proof of theorem B. And okay, so in the last minute, maybe if you have no question, I put some open questions that will be maybe interesting to think about. So the first one is, in some sense, if we forget about the contact structure, if we just look at the smooth setting, I would like to show that this kind of results cannot be expected. So it's really the contact distribution that gives enough rigidity to expect existence of unbounded distance. Okay, so more precisely, the question is the following, or I put it conjecture here. So if you take a closed submanifold inside M, and you take its isotopy class, so the space phi lambda for phi diffeomorphism isotopic to the identity, and if you assume that the dimension of your submanifold is small enough, so here strictly less than half the dimension of your initial manifold, which is the case, of course, for Legendrian, then I would like to show that an invariant distance on the universal cover of the isotopy class of lambda is bounded. So it's really the fact that we added the contact structure and that make the existence of unbounded distance possible. If we forget about contact structure, then it's not possible anymore. And actually, there is a similar results that was shown by Burago, Ivanov, and Polterovich, and also Tsoboy, not in the relative case, let's say, but on the group of diffeomorphism itself. Actually, they shown that on the group of diffeomorphism, isotopic to the identity, you cannot expect existence of unbounded B-invariant distance. And here it will be, in some sense, an analog of this result, but for the relative case. Okay, so this was one question. Another one, it's also based on, actually for the contact sphere, we know a lot of flexibility results. For example, Fraser, Polterovich, Rosen shown that for the standard contact sphere, if you look at the group of contactomorphism, then you cannot find any interesting B-invariant distance on this group. And again, a bit in the same vein, I would like to show that it should be the case also for Legendrian, but this I don't know, but it will be interesting to see if for any Legendrian on the sphere, you take the Legendrian isotopy class of this Legendrian, then you cannot find any invariant distance that is unbounded on this space. And maybe a last question, and actually all the thing I was talking about was for, no, not all the things, but all the unboundedness results for Legendrian was not on the Legendrian isotopy class itself, but for the universal cover of the Legendrian isotopy class. And actually, there is no unboundedness result, I think, for closed Legendrian, and for the Legendrian isotopy class itself, not going to the universal cover. Actually, it's easier to find unboundedness or rigidity results on the universal cover because you remember more about the Legendrian. You don't just remember the time one, you remember all the isotopy, or at least maybe not all the isotopy, but the homotopy class of the isotopy. So as you remember more, it's easier to construct, to have rigidity results. But if we forget about this whole isotopy, if we just think about the one Legendrian, then I think there is no answer to this question about unboundedness for Legendrian isotopy class itself. And so I think this was the three question I wanted to talk about. So thank you very much for your attention.
Thank you very much, Pierre-Alexandre, for your beautiful talk.
Thank you.
Would somebody like to ask already a question?
Maybe I have a little comment about this metrics on diffeomorphisms, right? So all is okay except dimension 2. Because in dimension 2, when you have surface of genus 1 or higher, so there is a result by Bowden, Hensel, and Webb, very non-trivial, highly non-trivial result, which shows that there are non-unbounded distances.
Ah.
And so, I mean, God knows, so maybe in small dimensions, like in dimension 3, something happens. So that's, I mean, in Legendrian case. So that's, I don't know, of course. Okay, but I mean, that's, yeah.
Thank you. I didn't know this. So
yes,
in
and there is
dimension
also some delicacy in dimension 4, which I don't remember. Probably in dimension 4, it's still unknown. But otherwise, indeed, it's unbounded. Yeah. Okay. So that's, yeah. And I have another question. I mean, when you prove that, I mean, you have this unbounded metric, so next natural question is, what is the coarse geometry of this metric? And so, for instance, kind of, is so true or not true that there exists embedding of a line, let's say quasi-isometric, such that all the group, I mean, all the space of Legendrians is in a neighborhood of 100 around this line. So can you prove or disprove this?
So can you repeat the question?
Yes.
Please?
So you have unbounded metric space. So in principle, this metric space could look like this, that you have like quasi-isometric embedding of R, and all the group lies in a neighborhood of radius 100 allows this line. And in symplectic case, so for instance, for diffeomorphisms of spheres, so there were several groups of people who kind of proved this with very hard work. Yeah, so I mean, this is not the case. So it's not, in principle, untrivial, non-trivial result, kind of, yeah? But for Legendrians, I have no clue what happens. And that's very, very natural question. So that's...
Yeah.
Yeah.
No, I don't know. I don't know. I don't know. Yeah.
Okay.
I would think that it's not only around the line. I would think it's bigger than that, but I'm not sure.
Yeah, but then I mean, it would be nice to prove this, maybe to find
Of
other
course.
flats, or I
Yeah.
mean, to work on asymptotic cone. So there is kind of this Gromov's asymptotic cone, which captures behavior of the space, like I mean,
Okay. Yeah.
when you look at it from very far away, yeah. So maybe you can do some calculations there. So in
Yeah,
symplectic
sure.
case, I mean, there is at least some examples of such calculation.
Yeah, no, of course. It's an interesting question. Yeah. Thank you.
Pierre, do you have kind of a natural conjecture to characterize Legendrians that admit an invariant unbounded metric? Is there, or do we know not yet enough to have an intuition for that?
I would say orderable is a good start, I think, at least.
Yeah.
Orderable. I think without orderable for the moment, even for metric on group of contactomorphism, also every time orderability is assumed. And boundedness, so this is, yeah, for unboundedness. And for boundedness, actually, there is a beautiful paper of Patrick Massot and Sylvain Court also about boundedness, also on the group of contactomorphism, where I don't remember exactly. I think they show that for contact manifolds that admit open book decomposition, such that the page of the open book is sufficiently flexible. I don't exactly remember what is the sufficient flexible condition. Then the group has to be bounded. So here, I guess similar statement can be done for Legendrian, but maybe a good start will be, yes, to try to start with the sphere. Try to start with the sphere to show that for the sphere it's bounded, and then see what we use for boundedness. Maybe also it allows to understand more what is important for unboundedness. But I would say that a good start for unboundedness, that orderability is an important condition. Maybe not sufficient, but maybe not necessary neither. But I think it's a good, yeah, good candidate to be a yeah, very important condition. Uh,
You. Are there other questions?
So Dylan wrote something in the chat. So
ah,
Oh yeah, thank you, Dylan.
there is the Shilukhin oscillation distance.
Yes.
Measure distance to rep flow. Oscillation distance, which measures distance to rep flow. Ah, that's true. Okay. And then this distance, you say that it is unbounded sometimes, and then it
But it's on the cover, right? Or
it's not invariant, right? So it depends on
right, it's not invariant.
yes, but the question
right.
is whether you can build. I mean, if you take some supermom or something, whether you can build something invariant. That's I don't know. So Igor,
Yeah.
can you comment about this?
Not sure. I mean, taking suprema usually does not really work because we don't know if it's bounded or not. But on the other hand, I'm pretty sure that so there are some methods that are used to prove that this kind of distance to rep flow, this kind of not by invariant distance to rep flow is unbounded. And these methods might be possible to apply to prove something like special cases of question 3.
So sorry, can you repeat, Igor? Sorry,
So it was a very long thing I said. I'm not sure.
yeah, sorry. No, what you said about dimension 3, what you can use to prove.
So there's this distance to rep flow, and in certain cases, it was proven that this distance is not bounded. And I think that if one looks into the methods that are used there, then one might be able to show something about invariant distances as well.
Yeah. I think so too. Yeah. Okay, thank you, Igor. Salut, Vincent. Hi.
So in the Hamiltonian setting, when one takes Finsler metrics, they are all comparable to Hofer, right? Now here everything is discrete. Is there a way still to normalize and maybe to see that all unbounded metrics are somehow comparable, or did people
No,
study such a thing?
no. I think there are really unbounded distances that are not equivalent. I don't know if it answers the question, but I have examples of unbounded distance, not on space of Legendrians, but on contactomorphism, such that, yeah, one of them is unbounded when you look at iteration of the rep flow, but the other one is unbounded for complete different reason. When you look at it on the rep flow, it's just, it's a constant, for example. So yes, I don't know.
So there is a much bigger zoo somehow.
Yeah. There are interesting invariant distance that are not yeah, equivalent, and yeah, they different. Yeah.
Vincent, you would like to ask a question?
No, not much. But thank you very much for the talk, Pierre-Alexandre.